Hello guys, welcome back to my channel, the Kimboy. In this video, I will be talking about introduction to EO modeling or equation-oriented modeling. So what is actually EO modeling? So EO modeling is the opposite version of sequential modular algorithm. So in this equation-oriented, the system or the simulation will be solved as a one big non-linear equations. So it is what make EO modeling is different from SM, because in SM we will solve the flow sheet incrementally for each equipment. So each equipment will have its own model. However, in this EO modeling, we will solve the entire flow sheet as a one whole equation. So yeah, it might be more consuming in terms of computing process, but later we will see in maybe the next video why this EO modeling is important and why it is still used in the commercial process simulation software, especially UniSim. Okay, so here I have an example of flow sheet that we will simulate today. We have a mixer, cooler, and also a compressor. So if we use sequential modular uh, algorithm, we will start to solve this mixer first, and then to the cooler, and then to the compressor. Yeah, it will be solved sequentially, as the name implies. So we could also know that if this stream is not converged, but this stream is converged, the problem is might be in this E100 or in this cooler. The same as well, if this outlet of the K100 is not converged, but the inlet is converged, we can guess that it might be the problem comes from the compressor. So it has more user-friendly troubleshooting ways compared to EO. Because if we have an EO flow sheet, if there is a problem, for example, with the compressor here, the whole flow sheet will not converge. So we actually don't have a clue which block is the main problem one. Yeah. So even though the mixer already well specified, the cooler well specified, the compressor is not well specified, the whole flow sheet will not converge. Yeah, because it is EO. EO approach. In EO approach, the flow sheet will be solved as a whole. So in order the flow sheet to solve as a whole, the DOF or degree of freedom should reach 0 for a whole of the process. So it is not a part of the model that needs to have a 0 DOF, but the whole model should be 0 DOF. By this concept also, we could imagine that one of the advantage of EO modeling is we have a more flexible specification. So for example, usually we will specify two specification here and one specification here. But we can transfer, for example, this one specification to the cooler, or maybe the specification we will move to the outlet of compressor. So we have a more flexible way of calculation, because the flow sheet will not look at the model by itself, but as a whole flow sheet. In SM modeling, we should obey that every model have its own DOF. So we need to supply enough information to each model. So here we have a more flexible way of specifying a specification in the model. Okay, so I think that's it for the introduction. Let us continue to the simulation. So here, because for the sake of example, I will use just a simple component. Yeah, for example, here I will use methane. Fluid package, I will use Peng Robinson. Okay, so for this EO operation, UniSim design have uh distinctive or maybe a designated block. Yeah, you can see here UniSim EO operation. You could add it from the model palette. Yeah. We can have a template or you can have a blank flow sheet here. I will choose the blank flow sheet because we will configure by our own. Another way is you can press F12 and then you can go to the subflow sheet and you could see that there will be UniSim EO operation. Okay, so you can click add here. Okay, now I will have two inlet stream. Let me name it as 1 and 2. Okay, yeah, we can add arbitrary number here. Okay, so we have two methane that coming in here. One is the colder one is the colder one, and the hotter one. Okay, then I will have a brief explanation about the feature in UniSim Design EO operation. The first one, we would like to see the parameters block here, parameters tab, sorry. We could see that we have an option to change the software type. Yeah, the default one is the sequential. So if the software type is sequential, it will be the same software that is used in the environment in UniSim Design. So if you want to go to the EO, you need to change it into the simultaneous software. And the third one is optimization. So this optimization is an EO optimization algorithm. Okay, so for now, let's continue. I will click this internal PFD. Yeah, so you could see UniSim EO operation have its own flow sheet. So flow sheet, and we have our own unit operation. Okay, so the first thing to add is mixer. I will add this by double click. Okay, then I will connect the inlet to the mixer by left click and drag. Okay, you could see that in sequential software, when we connect the inlet, yeah, we already converts it. And when we connect the second one, yeah, we also converts the simulation. Okay, we could adjust if we have more than two input here. Yeah. Okay. So another thing is you could see that it is not a must to have an outlet boundary nodes here. Yeah. So we don't supply any outlet here, but yeah, it is still fine in UniSim EO operation. So you could see that the block still converge. And we could see the condition of the outlet here. Okay, so this is the calculation of the mass and heat balance of the outlet. Okay, the next thing I would like to add a cooler. Okay, heat transfer, cooler. Now, beside double clicking the block that we want to add, we also could right click and drag, and you could see that it will connect automatically. Yeah. Here you can see that in sequential mode, even though the block of cooler is not yet converged here, but we are able to still manage to solve the mixer block. Yeah, even though our cooler block is not yet converged. Yeah, it is it is the uh, how sequential modular algorithm work. Okay, so if I change now the solver into simultaneous, you could see that the whole block is not converged. Okay, I will change back to sequential. Oh yeah, when you change into simultaneous, you could see that we need two more specification. The DOF is two. We need to have it zero. So we need an additional two specifications. Okay, so there are two approach here to solve EO operation block. The first one is we could make this flow sheet first as a sequential, and then we change it into EO solver. The second one is we will use EO solver from the first, but we will solve the flow sheet uh, incrementally. Yeah, so time model by model will be solved first to make the simulation calculation is not that hard. Yeah, to make the convergence is more easy to be achieved. Okay, I will try first to solve this in sequential mode. Now I will put specification. Yeah, the yellow one is the recommended parameter. So since the DOF is 2, I will supply two information here. The pressure drop and the delta temperature. You could see that the simulation is converged now. Okay, in the conditions. Okay, the inlet is 43, the outlet is 53. Yeah, it should be negative, yeah, because this is a cool. Okay, now the temperature become 33. Yeah. Now, if I change the sulfur type into EO, yeah, you could see that it's off. Yeah. For the third block here, the compressor, I will try to um, solve it in EO mode. I will go to the rotating equipment, compressor. Yeah. We have one DOF here. We have one DOF here. So let me set the pressurize or the pressure ratio as 2. Okay, you could see that we also able to solve the flow sheet in sequential mode, but yeah, sorry, in the EO mode. When I don't put this specification of pressure ratio, the whole flow sheet will not converge. Yeah, because we are in the EO mode. So if the DOF is reached, the whole DOF reach 0, the EO operation will start to calculate. Okay, now how if I want to have an outlet stream here that connects. So I need to have this kind of connection. And if we go to the PFD, where we'll have yeah, this one. Okay, so since we don't connect the stream, yeah, the whole flow sheet will not converge. Yeah, you could see that we have 4 DOF. 4 DOF is stands for the temperature, the pressure, or the vapor fraction, and then the composition and flow. Yeah, so it is the four for specification needed for the stream. Okay, because the EO flowsheet don't know that this stream number 3 is the outlet. It thinks that there is an inlet, so or yeah, maybe it's just a normal stream, so it requires 4 specifications. Now, if I connect this to the outlet, yeah, you could see that the calculation starts and converts. And here, if you could see at the outlet conditions, the temperature is 101, the pressure is 554. Now, let us compare with this. Okay, yeah, that is 101. The pressure is 554. Yeah, so the value inside the EO subflow sheet is propagated to this outlet. Okay, so I think that's it for our tutorial to EO modeling. I hope that you guys could apply this technique to your case or to your project. And see you guys on the next episode. Bye bye.